Data quality assessment rules are the third step in a comprehensive data quality analysis. Briefly, here are the definitions of data quality dimensions, data quality measures, and data quality rules. In this video, we focus on data quality rules. Data quality rules use the data quality measures calculated in a previous step. We previously showed how one could use the White Rabbit data profiling tool, or SQL, to calculate data quality measures. There is a huge commercial and open source marketplace for calculating data quality measures. Data quality rules express the acceptability of a data set based on one or more data quality measures. The limits set in a data quality rule may result in a simple warning, a more serious red flag, or a complete hard stop indicating issues that are so serious that the data are simply unusable under any circumstances. Rules also may be categorized by their scope. Global rules measure intrinsic data quality, which are global data quality properties that are not specific to a particular use case or analysis. Rules that are created for a specific use case are called fitness for use rules. Fitness for use rules are extremely narrowly scoped, looking at a narrow range of variables and values. There are an infinite number of potential rules that could be written for both intrinsic and especially for fitness for use. Thus, it is important to ensure that the key areas of data quality are examined so that the end user isn't overwhelmed by rule warnings that are not relevant to their needs. We show 3 different data quality rules from 3 very different data networks. The FDA Sentinel rule checks that a laboratory test called ALP, which stands for alkaline phosphatase, always has a numeric value. That is, there is a data quality issue if the test is inserted into the database without an associated numeric result value. The OMOP Achilles rule looks at the number of distinct diagnoses represented as condition occurrence concepts per patient. The Pediatric Health Information System, or PHIS, rule sets 2 thresholds for the percentage and the number of invalid cases before throwing an alert. Tiffany Callahan from the University of Colorado gathered over 1,100 data quality rules from 6 large data networks. These networks varied in size, participating organizations, years in existence, and approach to supporting data quality work. Using the Data Quality Dimensions framework developed by the Data Quality Collaborative, Tiffany categorized each rule. Some rules were categorized into more than one group so that the sum is larger than the number of rules. From this diagram, the largest number of rules assessed have features associated with atemporal plausibility. Value conformance and atemporal completeness came in 2nd and 3rd place. Here, you can see the data quality rules by category broken out for each of the 6 networks. Each bar represents 100% of that network's rules, even though each network had a different absolute number of rules. There are vast differences in the distribution of data quality categories that each of the networks are examining. There is no distribution of data quality rules that is optimal in all settings. Each network determines the rules that are most appropriate for their intended user base. This figure from Ritu Kar from Children's Hospital of Philadelphia shows the specific data quality errors seen in one of the networks in the Callahan paper. This figure shows that missing data greatly dominates the data quality errors seen in PedsNet. This figure, also from Ritu Khare, is a fascinating visualization of the changes in the types of data quality issues over time as the data network and data quality system matured. The x-axis represents different ETL extraction cycles over time, and at each ETL cycle, the bars represent the type of data quality issues found during that cycle. In the early cycles, ETL programming errors, represented by the red bars, dominated. But over time, these errors were fixed and were replaced by characteristic errors, which represent the blue bars, which now dominate. Characteristic errors reflect limitations in the data due to limitations in the source system and are not due to the ETL processes. Fixes to characteristic errors require the owners of the source data system to fix the stored data rather than anything that can be done by the ETL programmer. We take a slight detour to highlight the unfortunate limitation of the current state of affairs in data quality assessment tools. Currently, tools are tightly tied to the underlying source data model and to one-off methods for storing data quality results. The rules, reporting, and visualization tools that operate on these intermediate outputs are also tied to those data structures and therefore cannot be used by other groups who are using other data models. While still a research endeavor, the data quality community is attempting to develop a single common data model for storing data quality measures that are independent of the source data model. When this structure finally exists, writers of tools that provide data quality rules, visualizations, and reports can use this common data model, making their capabilities available to any system that writes their data quality rules into the data quality common data model. To summarize, data quality rules use data quality measures to determine the acceptability of a database or data set. Rules may examine broad data quality features called intrinsic data quality or very use case specific features called fitness for use. Different projects will develop data quality rule sets that inspect data sets for data quality issues that are most meaningful to their end users and use cases. We hope for a future state where data quality rules and tools can be used interchangeably. That day may not be far off, as a group of investigators are actively working on solving this problem.